Welcome to another explainer. Today, we're putting on our cosmic detective hats to uncover the origins of our very own neighborhood in the universe, the solar system. So grab your magnifying glass because this is honestly one of the greatest cold cases in all of science.
Okay, let's jump right into this ultimate mystery. Think about it for a second. If there was absolutely nobody around 4.6 billion years ago to observe the solar system being made, how can we possibly know what happened? We can't just go look up a historical record. We have to reconstruct the past purely from the clues left behind.
To solve this case, today's agenda is simple. 1. The solar system mystery. 2. Clues in the cosmos. 3. From dust to planets. And 4. Modeling the universe.
Let's start with Section 1, the solar system mystery.
The fundamental issue here is pretty obvious, right? No one was there to observe the solar system forming. Now, observe in science means actually watching something happen. Since we couldn't literally watch this massive cosmic event unfold, we can't run a simple experiment. We have to rely on the scientific method to piece the whole history together from the ground up.
So how do scientists actually solve a cold case like this? Well, they tackle it from two different angles. On one side, they look for evidence, which are the facts derived from modern observations. On the other side, they come up with a testable theory, a hypothesis, and then they look for evidence to support it. It's this constant, fascinating back and forth between what we see today and what we think happened billions of years ago.
Moving on to Section 2, Clues in the Cosmos. Let's see what evidence we can gather today.
When you map out the paths our planets take around the Sun, you can clearly see Jupiter, Earth, Venus, Mars all tracing these wide, distinct loops, which we call orbits. Just observing this current layout gives us some massive hints about our past. If you really dig into the facts from those observations, a striking pattern emerges. All the planets orbit the Sun in the exact same direction. Not only that, the Sun and most of the planets spin on their own axes in that exact same direction too. And to top it off, most moons orbit their planets in the same direction the planets are spinning. Everything is completely synchronized. It's almost like a highly choreographed cosmic dance where everything is spinning and orbiting in total agreement. And this brilliantly illustrates a crucial final clue. All the planets orbit the Sun in the same plane, just like all the objects sitting on a desk. This means our solar system isn't some chaotic 3D sphere of orbits buzzing around like a swarm of angry bees. It's flat. If you put the solar system on a table, all those orbital paths would lay completely flat against the surface. So whatever formed our system didn't just spin, it had to flatten out over time.
All right, Section 3, from dust to planets. With our clues gathered, let's build our hypothesis.
Our origin story begins with a nebula, which is simply a giant cloud of dust and gas in space. Imagine a massive, chaotic cloud of microscopic building blocks just floating out there in the deep, freezing vacuum. I know it doesn't look like much, but this is literally the raw material for everything we know.
And we aren't just making wild guesses here. Today, right now, scientists can point telescopes at places like the breathtaking Orion Nebula and actually observe distant young stars being born from these exact types of dust and gas clouds. We can literally see the process happening elsewhere in the universe.
Let's break down how this actually builds. It is basically a compounding snowball effect, completely driven by gravity. First, particles of dust and gas pull on each other with a really weak gravitational force. Next, as they stick together, their total mass increases. Then, because mass dictates gravity, that greater mass creates an even stronger gravitational pull. Finally, this stronger force violently attracts even more dust and gas, forming a rapidly growing ball. It's just a continuous, accelerating loop. As this massive ball grows and spins over millions of years, it naturally flattens out into a disk. Think about tossing spinning pizza dough in the air. It flattens as it rotates, right? Well, 4.6 billion years ago, our early solar system likely looked just like this, a glowing hot center surrounded by a massive, flat disk of swirling dust. And this beautifully explains our earlier clue. It perfectly answers why all of our planets orbit on a flat plane today.
So, the really crucial point here is what happens to all those separate clumps of matter spinning around. It basically comes down to a battle of scale, forming a star versus forming a planet. If a growing ball of dust and gas gets beyond a certain immense size, the internal pressure becomes so intensely great that it gets hot enough to ignite and become a star like our Sun. But if a ball gathers matter but never quite reaches that critical threshold, it just slowly cools down and becomes a planet. Just think about that for a second. Scientists actually think our own massive neighbor, Jupiter, was incredibly close to reaching the size needed to become a star. It was so close to igniting. If it had gathered just a little bit more mass from that original nebula, we might literally be living in a solar system with 2 suns. Wild, right?
Let's wrap things up with Section 4, Modeling the Universe. How do we test this?
Since we obviously can't build a universe in a laboratory, and we definitely can't wait a billion years to see what happens, scientists use incredibly powerful computer models. They program all the known laws of physics into a computer, start the simulation with a digital cloud of dust and gas, hit play, and see what it predicts. It basically takes a millions of years process and speeds it up to verify if our nebula theory actually works mathematically. And the good news, the models do indeed predict that a star will form, surrounded by a flat disk of planets.
But science is rarely completely perfect, and we've got a massive anomaly right next door. Remember when I said almost everything spins in the exact same direction? Well, Venus actually spins on its axis in the opposite direction. While Earth and most other planets are happily spinning one way, Venus is slowly, stubbornly rotating backward.
This backward spin totally contradicts our main hypothesis. To contradict means to go against something or oppose it. If everything formed from the exact same uniformly spinning disk of dust, why are Venus, and actually Uranus too, spinning the wrong way? It completely throws a giant wrench into that neat and tidy model we just built.
Which brings up a super important point, the limitations of scientific models. Models are amazing tools, but they are representations, not flawless copies of reality. They might not be entirely accurate, and right now, our basic models cannot fully explain every single contradiction, like Venus. But even though the vast majority of our evidence strongly supports the nebula hypothesis, these limitations remind us that science is just an ongoing, fascinating process of refining what we know. Which leaves us with this final, thrilling thought. If a fundamental model of our origins, a model backed by tons and tons of evidence, still can't fully explain why an entire planet is spinning backwards, what other mind-bending mysteries are just waiting to be discovered in our cosmic backyard? Keep looking up, keep asking those big questions, and thank you so much for joining me on this explainer. Catch you next time.